So what is a random variable? Probability theory is a really wonderful subject because it is something that is possible to understand intuitively without having a lot of mathematical background, but it is inherently a very mathematical topic. And so it allows a large population of people, and especially people who don't necessarily have a math background, to talk about math. And it's really wonderful because this is a really great theory. But along with this, because it needs to appeal to non-math people, when people talk about probability theory, and I'm specifically referring to random variables in this video because random variables are probably the most central topic to probability theory. When you go and you try to learn about random variables online, you get a lot of different explanations and a lot of different ways of talking about it. And part of this is from people who either don't have a mathematical background, like a rigorous measure theoretic mathematical background themselves, or are trying to appeal to an audience that does not have that background. And so if you want to appeal to a wider audience, you simply cannot use the most mathematically rigorous language because you're just going to lose people. And so you need to make sacrifices in your rigor in order to appeal to a wider group of people. And if those sacrifices in rigor allow people with less mathematical background to get a better understanding of probability theory and random variables specifically, then that's wonderful. But it can also lead to situations where you see random variables talked about slightly differently in different places and with different levels of rigor. The other aspect to this is even among people with more mathematical training, there are many different fields that use concepts from probability theory. Like statistics is sort of a separate field from probability theory, and then you have anything like engineering or physics or computer science. You have so many STEM fields in like biology and chemistry and so many STEM fields that use ideas from probability theory, and different academic disciplines tend to have their own flavors of languages and ways that they like to talk about things. And so it can be difficult to understand what exactly is being referred to in a particular discussion of random variables. And so you have situations where either there's different levels of rigor, there's different words being used, and even among the mathematically rigorous explanations, there are situations where it's not, sometimes it's so mathematically rigorous that it's not entirely clear how these mathematical ideas relate to actual applications. So if people are talking about IID sequences of random variables, it's not always clear, it took me a while to figure out, are they talking about, is each random variable here, is this just a random, outcome of something? And just the way that random variables can be talked about can be a little bit vague, and it varies from author to author. And so my goal here is to try to provide a more rigorous definition of a random variable, but to build to it from a non-rigorous definition and a concrete example. And my hope is that starting with that foundation will sort of clarify what the mathematically rigorous things I'm talking about are actually referring to. And I also hope that starting with a more of a lower level, something that's less mathematically rigorous at the start, I'm hoping that it can appeal to a wider audience and more people can sort of gain an understanding of what a random variable is. I will say that I am going to introduce more and more traditional mathematical notation as I go along. So it's going to start out with like examples and more simple like grade school and high school level concepts, but slowly but surely more like proof-based notation is going to come into play. But my hope is that regardless of what level you are at, you will at least get something out of this video and will gain some more understanding of what exactly a random variable is. Whether you haven't taken any advanced or any like college level mathematics courses at all, or if you've taken a course in measure theory. All right, so let's get into it. So the way I'm going to describe a random variable without mathematical rigor is that a random variable consists of three major things. We have events, we have probabilities, and we have outcomes. Now how are these three things related? Each event is going to have a probability and individual events have, to be consistent here, I'll say each individual event has an outcome. Okay. You might notice that I said event and then individual event. Later on, we'll see what that means. But intuitively, we just have events, probabilities, and outcomes. So, given that definition, let's look at an example. Okay. You have a coin that lands heads 60% of the time. When it lands heads, you get $2, and when it lands tails, you lose $1. Let X be a random variable that represents 2 coin flips. Okay, so this is an example of a random variable. So with this example, what are the 3 things we talked about? We have events, probabilities, and outcomes. So let's write this out. Events, probabilities, and outcomes. Okay, so what are the events? We have 2 coin flips. Each coin flip can be either heads or tails. And so we could get 2 heads, we could get heads and then tails, we could get tails and then heads, or we could get 2 tails. Now, what are the probabilities of these individual events? So if we get the first one, getting 2 heads, so we have a 60% chance of flipping heads. So the probability of getting 2 heads is 60% times 60%, which is 36%. Heads then tails, 60% chance of heads, and then 40% chance of tails. And that is going to be 24%. Similarly, tails and heads is going to be 40%, then 60%, so that's 24%. Then finally, tails and tails, 40%, then 40% is 16%. Okay, so we have a probability for each individual event, but we also have an outcome. So anytime we get heads, we get $2, and tails lose 1. So if we flip 2 heads, then we get $2 plus 2 more, that's 4. Heads and tails is going to be 2 minus 1, which is 1. Tails heads is going to be minus 1 plus 2, which is 1. Then tails is going to be minus 2. Okay, so a random variable, the random variable x here needs to encapsulate all of this information here, because basically that's what a random variable is. It describes the events, probabilities, and outcomes that can happen in a certain probabilistic situation. So we need to take this information and we need to write it down using mathematical language. So let's start. So to start with, we have these events. So we will let capital omega denote the space or the set of events. Let's use set. So omega is going to be the set of events. What else do we have? We have the probabilities. We said that each individual event has a probability. And so this relationship can be described using a function. So we are going to have P be a function that maps events, and the events will be lowercase omega in uppercase omega. So these are just going to be events in the set of events. So P is going to be a function that maps these individual elements to probabilities. And probability values, which we can see here, are just the percentages of the events happening. And what else do we need? So we've taken care of the events, the probabilities, now we need the outcomes. So each individual event has an outcome. I'm actually going to go back here. A function that maps events in omega to probabilities. And we'll come back to why that's important. But P is going to be the function that assigns probabilities to events. But lastly, we have our function x here that is going to deal with our outcome. Be a function that maps individual events. And here I will use this notation lowercase omega in uppercase omega. So these are just individual elements of the set of events. It's going to map these individual events to the outcomes. Okay, so now let's write down what is omega, what is p, and what is x. So to start with, omega is just, so we said that this is just a set of events. So it's a set, and it consists of 4 events. We have 2 heads, heads and tails and heads, and 2 tails. Okay. Now, what about p? So p is going to be a function that maps the events to probabilities. So we can just go back up to our table, and in the probabilities columns, we can just assign the values to p of the event that appears on this row. So here what we're saying is that p is a function that maps, it takes HH as an input, and it gives 36% as an output. So then this 24%, this is the value of HT, which is the same as TH. Then finally, this is the same as T and then T. Okay, so this is how the function p is defined. Each individual event here in omega has been given a value given by these 4 values. So this gives a complete picture of this function p and how it assigns probabilities to individual events. Lastly, we have our random variable x, and it's going to be, x is going to map the individual events to the actual outcomes. And so here in the first row, 4, this is the outcome of heads, and so that's going to be x of HH. Second row, this is going to be x of HT. It's going to be x of TH. Lastly, this is x of TT. Okay, cool. So there's one more thing that is missing here, though, and it has to do with this sort of subtle thing that I've been talking about like events versus individual events. So we want p to be a function that maps events to probabilities. Now, I'm going to call this really fancy cursive f. Let f be the set of all events to which we can assign a probability. Okay, so we know, okay, so this is every event that we can assign a probability to. Now we've seen that we can assign a probability to each of these 4 individual events. So for each lowercase omega and uppercase omega, this is also an element. This is also an event to which we can assign a probability. I am just going to use a notation here to say that this is just a set containing this value. Okay, so each individual element of this set of events, capital Omega, each individual event is as a set is in F, because we can compute the probability of each individual event. But we can also think about if we can compute the probability of collections of events. Also, let's say we wanted to probability of either heads or heads times tails. Well, what would this be? Well, the probability of two heads is 36%, and the probability of heads times tails is 24%. So we could define the probability of either of these two events happening as being the sum of their probabilities, which in this case would be 60%. So we would just say this is going to be the probability of heads plus the probability of heads tails, which is 60%. Okay. In fact, for any subset, let's call this A and say that A is a subset of omega. We can assign the probability of this event, of the probability of any event in this, the probability of any individual event in this set A happening is just going to be the sum over all events in A of the probability of that event. And that works intuitively in this simple example because we only have 4 events, and so this all works out nicely. So let's say if this subset capital A here, let's say it was heads or tails, then you would just add up these two values. So it would be 36% plus 16%, which is 52%. Should not have risked doing math in my head on the fly, because it is very easy to mess up. Okay. But yeah, and then if you wanted to do the probability of heads tails or tails heads or tails tails, you would just add these 3 values up together and you would get, what, 64%? No, that cannot be right. Yeah, that is right. That's exactly right. Okay, cool. Yeah, math on the fly is hard. Math is hard. Okay, so what this tells us is that, in fact, F with F being the set of all events to which we can assign a probability, it's going to consist of subsets of omega. And so that means that F is a subset of the power set of omega. Because the power set of omega is the set of all subsets of omega. And F is a collection of subsets of omega. And so it's a subset of the power set. And in fact, in this scenario, F is exactly equal to the power set, because any subset of omega we can find the probability of just by adding up the individual event, the probabilities of the individual events. Okay, so we've sort of given like we've sort of introduced abstractions to describe everything that's going on here. And so what we really have here is we have, what do we have? So we have x and x. Okay, and now I've been introducing mathematical notation, and now we're going to continue moving with it. So x, it's going to be a function, and the domain is going to be omega. This is the set of individual events. The range is going to be the set of real numbers, because we saw here all of the outcomes. These are all real numbers. But in general, for the purpose of abstracting here to the general definition of a random variable, we are going to keep in mind that in general, these outcomes could be any real values, because I could have given in this example, when it lands heads, you get pi dollars. So you could imagine that these outcomes could be could be like irrational numbers as well. And so, yeah. These outcomes are going to be real values. Okay, so we have a function, and it maps individual events in this set omega to the real numbers. But this set omega here, it also comes with, we also have this collection F, and this consists of subsets of omega. And we also have this probability, this function p here, that assigns probabilities to elements in F. So it assigns probabilities to subsets of omega. Okay. And so now this, and I'm going to introduce one more thing that we are going to talk about shortly. But now this is the notation that gives all of the information about what is involved with a random variable. This is the definition of a random variable. This shows everything that a random variable consists of. And so now let's actually write it out in words. So, definition. A random variable is a real valued Borel measurable function on a probability space. Okay. So, random variable, real valued, that's the R here. Borel measurable, that's the B here. Function, this is the function x, on a probability space, and probability space refers to this entire thing. Okay, now I'm going to erase this so that I'm not cluttering the screen, but this is everything that goes into the definition of a random variable. But now that we've given this very abstract definition, let's define every term that is in this definition. And then once we do that, we will sort of like meet back up with the ground up definition that we were given, or the example that we were building. Okay, so Borel measurable function on a probability space. Okay, so what is a probability space? Okay, we need to define a few things. So here, F is a sigma algebra, or sometimes called a sigma field. But when I learned about these first by reading Fallin's textbook on real analysis, and he typically uses sigma algebra, and so that's what I've stuck with. I think sigma field might be more common in probability theory, but whatever. Sigma field on omega. Omega is just any set here. We don't have really any restrictions on omega. But F is a sigma algebra or a sigma field on omega, meaning that F is a collection of subsets of omega, which means that's a subset of the power set of omega. So it consists of subsets of omega. It also needs to have this two other properties. The first of these property is that if we have an element A in F, then the complement of A is in F. So up here, looking at this example, if heads is in the events is in omega, then everything other than heads needs to be in F. And so the set consisting of heads tails, tails heads, tails tails needs to be in F. Okay, so complements. And countable unions. So if we have a sequence of elements in F, then the union from I equals 1 to infinity of AI is in F. And note, this was very deliberate that I wrote this A1, A2, ... and then union from I equals 1 to infinity, because and I'm actually going to write this out, countable. This is a countable union. It can be infinite, but it has to be countable. These definitions, this doesn't work if you allow this to be uncountable. And I'm not going to go into why. But basically, this is just like, if you have an infinite sequence, like a listable sequence of elements in F, then you can take the union of them and the result is still in F. By the way, from these definitions, you can see that the entire space, like the omega itself is going to be in F always. Any sigma algebra on omega will contain both, will contain omega, because I think you have to specify, I think you technically have to specify that, like, that it contains something, or that it's like non-empty. But basically, a sigma algebra is always going to contain the entire space and the empty set. Okay, but that's just a smaller point. So we have F as a sigma algebra here. Okay, so P is a measure, meaning P, so P is a function from F to real numbers that are greater than or equal to 0. So we have this. P of the empty set is going to be 0. And if we have events, a countable list of events in F, let me remember how to write, are disjoint, then we can compute the probability of their union by taking their sum. By taking the sum of the probabilities of the individual sets. Okay. P is it's actually a probability measure, which means that it is a measure and probability of the entire space is going to be 1, which is what you would expect from a probability space, because you would want the probability that some event happens is going to be 1, because that's the union of all the possible individual events. Okay, so we have this. Then we also have, finally, X is measurable. And technically the way we say this is FB. Oh, I have to say what B is. B is the smallest sigma algebra on R that contains every open set. And by open sets, I mean this in like the standard topology. So i.e. the topology generated by sets of the form A comma B, where A is strictly less than B, and A and B are both real numbers. Like it? Yeah. Okay, cool. So basically, and I'm not going to prove it here, but like you can prove that like there exists a smallest sigma algebra on R, and basically what you do is you just you take the intersection of all sigma algebras on R that contain every open set, and you prove that the intersection of this collection is itself a sigma algebra, and thus there does exist a smallest sigma algebra on R that contains every open set. Okay. Okay. So that's the Borel set, and then X is measurable. No, it is FB measurable. Well, given the context, we could have just said measurable, but to be more explicit, it's FB measurable, meaning that given any Borel set in B, if we take the inverse image of this set under X, we're going to get an element that's in F. Okay. So now this gives all the definitions of what's in here. A random variable is a real value, so it maps into R, Borel measurable function on a probability space. So we have a probability space, omega, which is just some set, F, which is a sigma algebra on omega, meaning it is a collection of subsets of omega satisfying these properties that I talked about. And we have a probability measure, P, which is a measure on F, which means that it maps values in F to not to real values greater than or equal to 0. And furthermore, it's a probability measure, meaning that the probability of the entire space is 1. So probability space, this taken care of. So Borel measurable function, so it maps into the real number. So the function x, it maps from here. So it takes an individual element of omega and maps it into R. And so then R also has this Borel measure, this Borel sigma algebra on it. And x is a measurable function, meaning that if we take any Borel subset of R, its inverse image is in F. And that's what it means to be a random variable. And so just again, tying this back to our example, omega here, these are just all of the, here, I should probably zoom out a little bit. Okay, yeah, so omega here, these are just omega consists of these 4 events. We have it defined here. F is a collection of all subsets of omega, and this is a sigma algebra. You can check the definition in this example and show that that lines up, that it is indeed a sigma algebra. I'm going to zoom in a little bit so that we don't have that weird cutoff at the bottom. Okay, P, we have this function P up here that we defined that allows us to define probabilities of individual events. But we also talked about how we can define the probability of any collection of individual events in omega. And the probability of the whole space, if you add all these together, you get 1. And so P is indeed a probability measure. Now we're mapping into R. Indeed, all of these outcomes are real values. And then this function is measurable. Okay, so how do we check this? Well, it's a little complicated, but just in short, a very basic way to see this, and you would have to prove that this is sufficient, but it turns out that in this case, you could just look at the inverse image of each of these individual outcomes, and that's because you could imagine that they're like surrounded by an arbitrarily small neighborhood, which is an open set in the Borel set, but we don't need to worry about the rigor here. To get a vague idea of why this function here that we've defined x, to see why it is indeed measurable, you take the inverse image of any of the outcomes. So inverse image of 4 is just this event HH. And that single event is a subset of omega, and so it is an element of F. And so there we go. If you take the inverse of -2, then you're going to get the set consisting of just tails, tails, and that is in F, because any subset of omega is going to be in F. And then if you take the inverse image of 1, then this is going to be the set consisting of both heads, tails, and tails, heads, which again is a subset. So this set consisting of 2 elements of omega, it is a subset of omega. And we said that any subset of omega is an element of f because they're equal. And so indeed this is an element of f. And so this function here, x, is indeed measurable. And therefore this example that we've given satisfies this mathematically rigorous definition that we've given down here. So in short, a random variable, I guess the other thing that I want to say here is that it's sometimes people will talk about random variables and talk about it as if it is like a single data point or a single outcome, like the outcome of a single experiment. And that's not really quite accurate, because what a random variable really encompasses all possible outcomes and all possible events, rather than just specific events that might be observed. And so there are some like tricky things here in how we sort of bridge the rigorous language into the more applied real world language of how you actually come across random events in the real world. But at the end of the day, from a mathematically rigorous perspective, a random variable is a real valued Borel measurable function on a probability space. And I hope that going through this process and building it up from this very concrete example helps to make this definition a little less abstract and a little bit more meaningful. And so I hope that you have a better understanding of random variables.